Good day, everyone. Our project topic is based on green hydrogen production on offshore platforms, and this will be taken by myself, Philomena, Wilson, and Vincent. Introduction. There has been a gradual shift from fossil fuel to renewable energy sources in order to reduce CO2 emissions, and renewable energy sources such as wind, solar, and biomass have been commonly used. Now, the challenges with these renewable sources is that they are intermittent in nature, and hydrogen, on the other hand, can serve as a stable fuel source. The offshore environment can also be utilized to produce green hydrogen because it has abundance of renewable energy resources. Hydrogen has also been considered the fuel of the future because it has outstanding energy efficiency and releases zero emission when burnt. Hydrogen also has higher energy content per mass as compared to gasoline and other fossil fuel sources. The aim of this report is to investigate the production of green hydrogen using the Hibernia oil platform located in Newfoundland and Labrador. For the site location, the Hibernia oil field, which is located at the southeastern part of St. John's, Newfoundland, is used. For the monthly average temperature, August has the highest monthly temperature of 14.93 degrees Celsius. For average wind speed, the annual average wind speed of this location is 9.25 meters per second. The highest wind speeds were recorded in December, January, and February. December was the highest with a wind speed of 11.39 meters per second, while August was the lowest with a wind speed of 7.28 meters per second. For the daily radiation from the sun, the annual average was 3 kilowatt hour per meter square per day. June had the most radiation, while December had the least. For the system architecture, the image depicts the structure of the system, and from the image, you can see that the electrolyzer, the PV panel, the battery are on the DC bus, the wind turbine is on the AC bus. We can see the hydrogen tank and how it interfaces with the electrical load and the converter. Now, for this report, we are considering three scenarios in order to determine the most suitable energy system. For case A, we are considering a PV converter battery system. For B, we're considering wind turbine converter battery system. And for case C, we are considering a hybridization of PV, wind turbine, converter, and a battery system. Now, an electrical load of 11.25 kilowatt hour per day was chosen, and this was based on the requirements of the offshore platform to power lighting and other minor electrical loads. For the energy system components, we have the PV panel, wind turbine, converter, battery, electrolyzer, and the hydrogen tank. Their specific rating, efficiency, lifespan, capital cost, replacement cost, and operations and maintenance cost per year are listed in the table. The Homer Pro optimization software is used to investigate the most suitable energy system for the green hydrogen production. In order to determine the most suitable energy system, parameters such as net present cost, levelized cost of energy, and utilization of the electrolyzer are very crucial. The net present cost of a system is the present value of all the costs the system incurs over its lifetime minus the present cost of all the revenue it earns over its lifetime. The levelized cost of energy is the measure of the average net present cost of the energy generated over its lifetime, while the electrolyzer utilization represents the total hydrogen produced under given circumstances as a percentage of the maximum possible hydrogen quantity that could be produced. Now, based on the inputs we provide to the Homer software, it can optimize the energy system based on the lowest NPC cost for the various scenarios. results. From the trend we can see the NPC and LCOE for the various cases, and we can see that KC generated the optimal result from the Homer optimization tool because it's produced the lowest NPC of $4.2 million and the lowest LCOE of $0.135 per kilowatt hour. Case A generated the highest NPC of 7.3 million and the highest LCOE of $0.339 per kilowatt hour. Now, for quantity of hydrogen produced, again, we could see KC also recorded the highest electrolyzer utilization of 86.2%.
Thank you, Mina, for the presentation. Now we're going to look into the process description of water electrolysis used for green hydrogen production. Currently, there are diverse methodologies for producing green hydrogen, but our project is focused on the utilization of hybrid energy systems from the offshore environment of Newfoundland and Labrador to serve as the energy feed for the water electrolysis process, which will be used for green hydrogen production. As earlier said by Mina, the offshore environment in Newfoundland and Labrador upholds abundance of renewable energy resources that could be blended in a hybrid manner to serve our water electrolysis process. Now, the choice of water electrolysis is because it is a viable way to truly produce green hydrogen. And the three most well-known electrolysis methods are the alkaline electrolysis, the polymer electrolyte membrane electrolysis, and the solid oxide electrolysis. For the purpose of our research, we are definitely utilizing the alkaline electrolysis due to specific reasons. It's one of the oldest and the most studied methodologies for water electrolysis process, and in this research, an integrated process route is employed in the simulation work for the synthesis of hydrogen from water split electrolysis by using Aspen-Heis's simulation method. In continuation, for the alkaline water electrolyzer, which was chosen for this research, specific characteristics were very valuable in enabling our choice for the alkaline water electrolyzer. The first is its high technological maturity. This is followed with the fact that it has a relative inexpensive capital cost. It's rugged in nature considering the environment we will be utilizing it, and then it also ensures large-scale hydrogen flow rates. Now, using the alkaline electrolyzer specifically, there are parameters utilized for this particular project that are very critical to the success of the water electrolysis process. And this includes the rated power of the electrolyzer, the area of the electrode, the feed rate, the electrolyzer operating temperature, the electrode overvolt, and then the number of electrons per reaction. In addition to the electrolyzer parameters stipulated for this particular water electrolysis process, it becomes important for us to have a deep insight into the process simulation parameters that would be utilized in the course of the Aspen-Heis's simulation for the water electrolysis process, which in turn will help in the generation of hydrogen from the offshore environment. Key parameters from this process simulation variables includes the gas separator parameters, the hydrogen and the oxygen cooler, including the CO2 compressor parameters. More importantly, the electrolyzer working conditions, temperature, pressure, and net duty parameters are also clearly stipulated here, including the stoichiometry of the entire process. It's important to have an oversight of this because these variables will be utilized for the Aspen-Heis's simulation process. For the effectiveness of water electrolysis process for the generation of hydrogen, it becomes very critical and efficient to carry out a sensitivity analysis using the Aspen Plus simulation to give an insight into the key variables that affect the overall performance of the quantity of hydrogen produced. Since sensitivity analysis involves an analysis into how the target variables are affected by the input variables. For hydrogen production specifically, temperature from this graphical analysis from Aspen-Heis's shows to have a direct impact on the quantity of hydrogen produced. Graphically, from a temperature of above 42.5 degrees Celsius, we saw an increase in the hydrogen production rate, which remained constant till a particular period of the hydrogen production process offshore. Specifically, pressure also has a critical role on the quantity of hydrogen being produced during water electrolysis process. From the graph we have here from the Aspen-Heis's simulation, we observe that at a pressure of 11 bar, hydrogen production took off effectively, and this continued at a consistent rate throughout the period of the water electrolysis. Thirdly, a critical sensitivity analysis carried out in this work was a sensitivity analysis on the effect of the water flow rate and the quantity of hydrogen being produced. From this sensitivity analysis carried out using the Aspen Plus simulation software, we're able to understand that the water flow rate has a direct impact and relationship on the quantity of hydrogen produced. Therefore, for us to anticipate a higher quantity of hydrogen produced, we need to be able to ensure that the water flow rate into the electrolyzer system remains consistent over time. And this should have been done when a desalination process has been effectively carried out. This is to ensure effectiveness in the quantity of hydrogen produced and to ensure that there is a reduction in the corrosion in the entire system. Electrolysis product. Process diagrammatic representations for the water electrolysis has been viewed from this particular slide. We get to see that the fresh saline water from the offshore environment gets into the fresh saline water heater to enable the temperature build up to the desalter working temperature. And thereafter, the consecutive products leave from the desalter bottom where it is being electrified, and then it moves over to the second Aspen design simulation here shows the incorporation of a cooler at the end of the process. This is to ensure that the produced hydrogen is being cooled for storage and transportation processes. The process and instrumentation design is indeed one of the very vital sections of the water electrolysis process design. This is because it gives us a deep insight into the instrumentation interconnectivity of all the process equipments and how the design takes place from start to finish. This particular process and instrumentation design is very important because it shows the water split electrolysis of the saline water for the non-recycled route for hydrogen production. In this particular route, the fresh water comes in from the offshore environment of Newfoundland and Labrador at a temperature of 25 degrees Celsius, and it's being heated up at the freshwater system heater to build up its temperature from 25 degrees Celsius to around 120 degrees Celsius. When it gets into the desalter, the products leave at the top and gets into the electrolyzer feed, and the process continues for hydrogen production. Desalter. Salination process here was also viewed, but for the P&ID process here, the non-gases were being recycled back. This is to ensure effectiveness in the process of the hydrogen production, which we observed that it got back into the desalter at a temperature of 90 degrees Celsius and at a pressure of 5 bar. Finally, on the process and instrumentation diagram, we also understood that it's important to insert a cooler into the system. So on this particular process and instrumentation diagram, a cooling system was included that should be able to cool the compressed hydrogen that has been produced from the water electrolysis process. This will enable it to be effectively stored for transportation systems and then fed into the electrical grid that will be utilized by the various communities in Newfoundland and Labrador.
Thank you, Wisin. Talking about the result and recommendation based on our project, the combination of solar PV and wind turbine, as in case C, gave the most optimal results for the energy system. Case C recorded the lowest MPC and LCOE, while the optimum operating temperature of electrolyzer is between 43.75 to 50 degrees Celsius. Yeah, case C has the highest electrolyzer utilization of 86.2%. The optimum operating pressure of the electrolyzer is between 10 to 11.2 bar. Finally, in the future research areas, the future areas include hydrogen market analysis, offshore pipeline network analysis for hydrogen transportation, hydrogen energy storage system, underground hydrogen storage. Thank you.